So let's start with the introduction. So what does exactly the word mean by sonar? Sonar is an acronym that stands for sound, navigation and ranging. From a physics perspective, its core mechanism relies on an acoustic wave or sound wave. We emit this wave into the water to navigate through the deep, communicate across vessels and detect hidden underwater objects. Now, you might ask, why do we use sound instead of traditional radar or camera? This comes down to fundamental environment problem. In the deep ocean, electromagnetic waves like light and radar are quickly absorbed and scattered, leaving them useless after just few meters. Sound, however, thrives in this environment because water is much denser than air. Sound waves travel incredibly fast, roughly 1,500 meters per second, which is about 4.5 times faster than sound travel in the air. As you can see in this picture, it is fascinating to note that humans didn't actually invent this. Our technology is a direct result of biomimicry, where we copy solutions from nature. Long before naval engineers built the first sonar array, animals like bats and dolphins had already evolved to use echolocation to safely navigate and hunt in pitch black or murky environment. So we simply took nature's brilliant design and turned it into engineering. Now let's look at the history of the sonar technology. For centuries, sailors navigated the deep ocean blindly by dropping heavy rope over the side of the ship to physically feel for the seafloor. The invention of the sonar completely changed the marine navigation by teaching us to see with sound. Now let's look at the timeline of discovery. The first one is 1490, where Leonardo da Vinci discovered that placing a long tube in the water allowed him to hear distant ship engine. This was the earliest form of passive sonar. The second one is 1826, sound speed calculated. Scientists using an underwater bell in Lake Geneva proved that sound travels through water at roughly 1,435 meters per second, about 4 times faster than in the air. And from 1912 to 1940, the Titanic disaster, the tragic sinking of the Titanic created an urgent need to detect icebergs. In response, the engineer Reginald Franzender built the first oscillator capable of bouncing an acoustic echo of an iceberg 2 miles away, proving that active sonar was possible. From 1950 to 1918, World War I necessity. To encounter deadly German U-boat submarines, French physicist Paul Lejeune used quartz crystal to generate high-frequency ultrasound pulse. This became the world's first operational system to actively locate the hidden underwater threat. And lastly is 1942, where the birth of the sonar. After years of this secret British development under the code name ASDIC, the US Navy officially formalized the term we use today during World War II, that is sonar, sound, navigation and ranging.
Okay, let's begin with the core physics principle. What exactly is sound? Sound is a form of energy that is produced when an object vibrates, causing particles in the surrounding medium to move back and forth. Classically, we categorize a sound wave as a mechanical wave. This means it physically requires a medium such as solid, liquid, or gases to transfer energy through the vibration of particles. It cannot travel through a vacuum. Furthermore, it is a longitudinal wave, which means the particle of the medium vibrates parallel to the direction that the wave travels. As the wave moves, it creates alternating regions of high pressure called compression and low pressure called refraction. This brings us to the importance of sounds in underwater technology and marine life. Unlike radio wave and light, sound can travel much farther underwater. Radio signals are quickly absorbed by water, while light cannot penetrate deep into the ocean. Sounds, however, travel faster and loses less energy, making it the most effective way to communicate, navigate, and detect objects underwater. This is why sonar uses sound waves. Interestingly, marine animals were using a natural form of sonar long before humans invented it. Whales and dolphins use echolocation, where they produce sounds and listen to the returning echoes. They use sound for communication, navigation, hunting, avoiding predators, and also finding their mates. In the deep ocean, sound is often more useful than a sight. Next, once the echo returns, sonar uses a simple formula to calculate distance. We use the speed of sound in the water and the time taken for the echo to return. The formula is distance equals velocity multiplied by time divided by 2. We divide by 2 because the recorded time includes both the journey to the object and the journey back to the receiver. Imagine trying to see in the dark depth of the ocean. Instead of using light, sonar uses sounds. A transmitter sends out ultrasonic waves that travel through the water. When these waves encounter an object, they reflect as echoes. The receiver captures these echoes and a computer calculates how far away the object is. In this way, sonar allows ships and submarines to see underwater using sound. As we explore deeper, sonar systems are divided into two distinct operating modes, which is active sonar and passive sonar. Active sonar dynamically emits a pulse and analyzes its echoes. This allows operators to determine an object's exact distance, vector direction, and relative size. It is perfect for mapping the ocean floor or tracking schools of fish. Passive sonar, on the other hand, is completely silent. It does not transmit any sound wave at all. Instead, it uses a highly sensitive underwater microphone called hydrophone, strictly to listen the acoustic signature, like engine vibration or propeller noises, already being produced by other ships or submarines. This is vital for military operation, where remaining undetected is crucial. To summarize the core differences between the two systems, let us look at this feature comparison metric. Active sonar actively sends out of a sound pulse, meaning it reveals its own position to anyone listening nearby, but it gives an instantaneous accurate measurement of distance. Passive sonar sends nothing out, keeping the operator completely hidden, but requires complex acoustic analysis to guess where an object is placed, purely on the incoming sounds. Both play vital complementary roles in modern maritime navigation and also defenses.
Now, for application of sonar technology, the first one is Navy and military. This is used for submarine detection and underwater surveillance. Submarine use active sonar to emit a ping to find target, and passive sonar listening silently to avoid detection. The second one is commercial fishing. It is used specialized sonar called fish finder. It is detect the acoustic difference between water and air-filled swim blender inside fish, mapping out exactly where a school is hiding. And third one is ocean mapping. Use multi-beam sonar to send out a wide fan of sound wave. It measure how long the echoes take to return to chart deep sea trenches, underwater mountain, and topography in the 3D. And the fourth one is marine research. Scientists use passive hydrophone array to listen to the ocean non-invasively. This allows them to track whale migration routes and study marine mammal communication without disrupting the ecosystem. And lastly is search and rescue. It is used side scan sonar to create highly detailed photolite acoustic image of the seafloor. It is very crucial for locating submerged missing vehicle, downed aircraft, or shipwreck debris filled in the mercury water.
I will explain the advantages and limitations of sonar technology. First, let's look at the advantage. The first advantage is that sonar works effectively in dark, deep or muddy water. Since sonar uses sound waves instead of light, it can still detect objects even when underwater visibility is very poor. This will make it more reliable than camera in many underwater environments. The second advantage is its long detection range. Sound wave can travel long distance through water, allowing sonar to detect objects that are far away. Because of this, sonar is widely used for navigation, military surveillance, and underwater exploration. Another advantage is accurate underwater detection. Sonar can determine the location, distance, and depth of the underwater objects with high accuracy. It can be used to detect submarines, underwater obstacles, school of fish, and even the shape of the ocean floor. Despite these advantages, sonar also has some limitations. So one limitation is noise interference. Underwater environments contain many sources of sound, such as waves, ships, and marine animals. These sounds can interfere with sonar signals and sometimes reduce the accuracy of the results. Another limitation is its impact on marine animals. Some marine animals, especially whales and dolphins, depend on sound for communication, navigation, and finding food. Powerful sonar system may disturb the natural behavior and affect the habitats. The final limitation is the high cost of equipment. Advanced sonar system require specialized technology and regular maintenance, which can be expensive. This may limit the use for smaller organizations or research groups. Okay, now let's move on to the future of sonar technology. As technology continues to develop, sonar systems are becoming more advanced and efficient. One important development is AI-integrated sonar. Artificial intelligence can help process large amounts of sonar data much faster than humans. AI can recognize patterns, identify underwater objects more accurately, and reduce human error. This will make sonar systems smarter and more reliable. Another exciting advancement is the use of autonomous underwater vehicles, or AUVs. These are robotic vehicles that can operate underwater without a human pilot. Equipped with sonar system, AUVs can explore dangerous or difficult to reach areas of the ocean while collecting valuable data. Sonar technology will also contribute greatly to deep sea exploration. Scientists believe that a large part of the ocean remains unexplored. Improved sonar system can help to create detailed map of the ocean floor and discover new underwater features, marine species, and also natural resources. In addition, sonar can be used for environmental monitoring. Researchers can use it to study marine ecosystem, track fish populations, monitor coral reefs, and observe changes in the underwater environment. This information is important for protecting marine life and supporting conservation efforts. To conclude, sonar technology is based on the principle of sound wave reflection. By sending sound waves through water and analyzing the returning echoes, sonar can detect, locate, and identify underwater objects. This technology has become an essential tool in many fields. It is used in military operations to detect submarines, in navigation to avoid underwater obstacles, in the fishing industry to locate fish, and in scientific research to study the ocean and marine life. Throughout this presentation, we have learned how sonar works, its application, its advantages and limitations, and the exciting possibilities for its future development. As technology continues to improve, sonar systems are expected to become more accurate, intelligent, and environmentally friendly. This will allow humans to gain a better understanding of the underwater world while supporting exploration and conservation efforts. Without sonar, much of the ocean would remain unexplored and our knowledge of underwater environments would be far more limited. Thank you for your attention.